this is your video for 6.1, Estimating with Finite Sums. Before you go through and watch this video, I do want you to read over the introduction in your textbook, Accumulation Problems as Area. That's on page 269. This part below about putting a program on your calculator, if I see you in person, I will put that program on your calculator. Otherwise, I found an online one that does a good enough job to get through what we need it for this section and for the chapter. These RAMs that we're going to be working with, because we're going to be looking at left and right Riemann approximation methods, you won't actually need the program for the AP exam. However, you will need to know how to calculate small ones by hand, so that is something that we are going to focus on. But again, if I see you in person, I will put that program on your calculator. Otherwise, use the online one that I've linked to. I'm actually going to skip this first example that deals with snowfall. Basically, what you're doing with this one is you're graphing the rate, and then you're calculating the area underneath the curve, and that's going to give you the total accumulation of snow. I believe there's actually a typo in the book because they don't have the correct answer for that. However, in the book video, there is a really great example that does illustrate this process. And again, this kind of goes along with that introduction to accumulation as area that is on page 269. So we're actually going to pick up here with example 2. So the particle starts at x equals 0 and moves along the x-axis with velocity v of t is equal to t squared for time t is greater than 0. We want to know, where is the particle at t equals 3? So we are looking for the accumulation of all the velocities, which will give me a total position for this particle. So first thing I need to do is actually graph v of t is equal to t squared. So at 0, I'm at 0, 1 is 1, 2 is 4, 3 is going to put me up at 9. So this is going to look like that. This does not tell me how many subintervals I'm going to divide this into, but for my purposes here, I'm actually going to use 12 as my subinterval. So if I cut this from 0 to 3 into 12 different pieces, each piece is going to be 1/4 wide. So I have 12 pieces. Each one is going to be 1/4 wide. This is not something we can easily find the area of. You could kind of count up rectangles and see, like from 1 to 2, that's a rectangle, so there's 1, and then 2 to 3 is another 1, and then going up is 1, going up is 1, going up is 1, so 1, 2, 3, 4, 5. So I know I have at least 5 whole rectangles, and then some other pieces that I can put together. So that gives me at least a starting point, but we can actually take this shape and create rectangles that match our curve in order to actually get a better estimate of what's going on here. So I'm going to go through and I'm going to divide this. I'm going to divide this into equal pieces. We are actually, if I were to divide this up, let's see. Here's my halfway point. Not the best here. Halfway point, halfway point, halfway point. So you can see there, I divided that up. Now from 0 to 1, I have 4 different rectangles here. In order to, actually, I'm going to do this a slightly different way. In order to get the best idea of what's going on, I'm actually going to use the midpoint. So I have that, and that, and that. So the rectangle from 0 to 1/4, the rectangle from 1/4 to 1/2, the rectangle from 1/2 to 3/4, and the rectangle from 3/4 to 1. So I want to actually look at halfway between 0 and 1/4, and that's where I'm going to draw my rectangle. Halfway between a fourth and a half, I'm going to meet the graph and then draw my rectangle. Halfway between a half and 3/4, I'm going to draw my rectangle. You see how part of the rectangle is above and part of the rectangle is below? And there's my other one. And I would continue that process the whole way through. So there's my halfway in each of those, my halfway in each of those. And these are probably going to get sloppier as they get bigger, but I want you to see the idea of what's going on here. So, halfway between. So you can see each of the rectangles that I draw has a piece above, a piece below. If I find the area of all of those rectangles and add them up, it's going to give me a pretty decent approximation of my area under the curve. So I'm just going to pull out the very first one from 0 to 1, the one that I wrote out. So I have a subinterval from 0 to a fourth, from 1/4 to a half, actually I'm going to drag these down here so I have some more space. 1/4 to a half, 1/2 to 3/4, and then 3/4 to 1. The midpoint of each of those intervals, from 0 to a fourth, the midpoint is 1/8. From a fourth to a half, the midpoint is 3/8. From 1/2 to 3/4, midpoint is 5/8. From the midpoint of 3/4 to 1 is 7/8. So you see that all of the denominators are 8, and my numerators are going up to the next odd number, and that's going to continue. So the next midpoint would be 9/8, and then 11/8, and then 13/8, and so on and so forth. The height of each rectangle is going to be plugging in the x value into the function. So my height is 1/8 squared, which is 1/64. This one is going to be 3/8 squared, which is 9/64. And then I'm going to end up with 25/64 and 49/64. And that's going to keep going. Again, I have that odd number in the top. Again, the width for each of these is 1/4, because each rectangle has a distance of 1/4 on the bottom. So to find the area of each rectangle, it's going to be your height times your width. Instead of height, if you wanted to call it length, you could do that as well. But you're going to multiply, rectangle is length times width. In this case, height times width. It's 1/4 times the height. And I have 12 different rectangles here, so I have to add up all 12 areas, and that is going to give me the area underneath the curve. Because all of these are multiplied by the same width, I can pull the 1/4 out and multiply it at the end. This is something that you will see on the AP exam, but instead of giving you the same interval in between, or the same width between your intervals, there are many times where they will change it up, and I am going to be pulling some of those examples so that you guys can see what those look like, so you'll be prepared when they come up on the AP exam. So we have 1/4 times, again, I have the 1/64, the 9/64, the 25/64, the 49/64, The next odd would be 9. When I square that, I get 81. And then I take 11, and then 13, and then 15, and then 17, and then 19, $21, and 23. So if we add those up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total rectangles. Whenever I add those up and then multiply by the 1/4, we get 2,300 over 256, which is approximately equal to 8.98 units. So that means the particle has moved about 9 units in 3 seconds. So it's moved about 9 units in 3 seconds. Now the actual integral from 0 to 3 of x squared is 9. So this is actually very, very close to what the actual integral is. And that's why this is useful to calculate the values of things that you can't just take the antiderivative of. Whenever you're measuring real values, you're not always going to be able to come up with some type of equation that models it and then take the integral of it. Sometimes you have to use these Riemann, these estimation methods in order to get a good picture of what's going on. So these are some pictures that go through and illustrate what the left and the right and the middle endpoints are going to look like. So at the top left, that's your left endpoint. So I kept this easy. I said I was going from 0 to 5, and I did try to draw the same picture for each of these. I know they look a little bit different. But for left endpoints, you are going to use the left value of your interval to plug into the function. So you can see here all of these rectangles, the left corner touches the function and the right corner does not. So whatever approximation you're doing, whether it's LRAM or RRAM, that's what should be touching the curve. For the right endpoint, notice for each of those, you're going to be using the right value. So it's the right corner that's touching the curve, the left is not. And then midpoint, which is what we just did in the previous example, the left and right do not touch, but it's actually the middle of the rectangle that touches. So you would be plugging in the value that's halfway between each of your intervals. So in example 1, we use the midpoint rectangle approximation method. We have the left and the right as well. Typically, the midpoint is going to be more accurate with smaller numbers. However, if you use a huge number of rectangles, so if your number of rectangles goes up to maybe 1,000, maybe 10,000, the left and the right and the middle are actually going to get closer and closer to the same value. On page 272 and 273, there is a chart that has some figures and some numbers using those different approximations. And it does show you how your estimations are going to get closer together when you use those higher numbers of rectangles. So this brings us to example 3. It says estimate the area under the curve of the function given below from 0 to x equals 0 to x equals 3. This is where your computer program is going to come in. So I'm actually going to hop onto my computer and bring that up. So again, this website is linked to the current assignment that you have for 6.1. So it is the Riemann sum calculator. Notice the way that Riemann is spelled. It is R-I-E. If you do end up with the program from my calculator, whoever I got it from years ago misspelled it and has it R-E-I, and I'm not sure how to change the spelling without messing up the program, so I've kind of left it alone. So anytime you need to do this calculation, notice it says here, if you have a table of values, see the Riemann sum calculator for a table. So we don't have a table, we actually have a function. So I'm going to click in this function place, and I'm going to type in x to the second power, and then sine of x. Lower limit, so that's going to be your lower value, which in our case here is 0. Our upper limit is 3. And then the number of rectangles, I'm going to start with 5. And then you can choose here, we want the left Riemann sum. If you're completing the whole table, you do need to do left, middle, and right. You can click here and toggle between right and midpoint. And trapezoidal, we actually won't talk about that one until 6.5, so that'll be at the very, very end of chapter 6. Then we come down here, do calculate, and what it does, if you scroll down here, it actually goes through the math behind what you would have. So we have 5 rectangles using the left endpoint. And so our approximation down here is this number here, 5.1548. Your book actually stops at 5 decimal places, so they stop after this 0, which I guess with the 5 there, it should be a 1. But this is the number that you would want to put into this box right here. So this box, that's where you'd put the 5.15480. So let's go back and do another one, because we can come back. And this is nice because you don't have to go back and change the function. All you have to change is, say, the number of rectangles. So let's skip 10 and let's go to 100. Again, I come down here and press calculate. It does the math and then gives me my solution. So that's the 5.75701. So there's your calculation for that. Let's say I just want to change my RAM method. So I'm going to go to midpoint, and I'm going to keep everything else the same. And then it goes down through and does my calculation for me. So this one, 5.7769, and then your book stops and makes this a 7. So you can see that with the 100, the left RAM was 5.7 and change. This one is 5.7 and change. So they're getting closer and closer together. And if you do 1,000, it's actually going to be even more accurate. So you could use this to fill in that table. Anytime they ask you to find an approximation using a RAM without specifying what your n is supposed to be, again, n up here, n is going to be the number of rectangles. If they don't specify that, you want to use a huge number. So you want to use, 500, use 1,000. Don't make it too big, because if you do make it something like 10,000 or 100,000, you may be sitting and waiting for quite a bit for your machine to actually go through and calculate whatever you're trying to find. But I know there are some questions in your textbook where they just want you to find an approximation, and they don't specify how you are supposed to do that. By the way, if you want to know the full numbers for those tables, or for that table, it is in your textbook, so you can go through and use that to check to make sure that you got the right values for there. So the next thing we're going to look at, this visual representation of RAM approximation, typically focuses on area, but our original motivation was looking to find distance traveled with a non-constant velocity, although for this one we're going to estimate volume. And I am going to use that same program that we did before. If I want to look at a sphere that has radius 4, if I put the center of a coordinate plane in the center of the sphere, you're basically taking the function the square root of 16 minus x squared, and you are rotating that or revolving it around the x-axis from -4 to +4, because this distance here is going to be 4. So if we want to divide those into, it says n subintervals of equal length. Notice that each slice here, if I look at the radius here, that distance is going to be the square root of 16 minus x squared. So if I want to know the volume here, so this is a sphere. If I'm slicing it, if I slice the sphere, I'm going to end up with a cylinder. Because if I take 2 slices of the sphere, they're going to have a width, they're going to have, the area of that circle base. And so for a cylinder, the volume is pi r squared h. So that's going to be pi times the square root of 16 minus x squared, and then times my delta x. Delta x is going to be whatever the width is, and we are going to look at a couple of different values, so I'm not actually going to put something in for that. So my RAM function here is going to be pi times, if I take a square root and I square it, I'm just left with what's inside. And then I'm going to leave off the delta x because the delta x is what I'm going to change for my number of slices. So number of slices, and then I'm actually going to do an MRAM on this. I know it doesn't actually tell me to do an MRAM, but if I want to get something that's accurate, I want to use MRAM because of the 3, it's going to be the most accurate, especially for smaller numbers. So I'm actually just going to write these values in here. Again, you would want to go back and do the same program that we did for the previous one. So if I use my n to be 10, and again, my a would be -4, b would be +4, I get 269.42299. If I do 50, I get 268.29704. If I do 100, I'm sorry, this one is not right. That one is 4. I skipped 25. So let's go back and fix that one. The number I just wrote there, that would be what you got for 25. This one is 13619. For 100, I get 268.09598. And then for 1,000, 268.08271. Notice that there's not a whole lot of change between 100 and 1,000, which leads me to believe that that's actually going to be pretty accurate. The actual volume of a sphere with radius 4 is 268.08257. And then there's a 3 and a 1 after that. So you can see it's actually very close. So those are very, very close together. So the approximation at 1,000 is actually very close to the actual value for this. The last thing that we have here deals with cardiac output, and I'm not actually going to go over this question here, but I am going to talk through this a little bit. So on page 275, they talk about cardiac output. And it says, estimate the cardiac output of the patient whose data appears in the table, in tables 6.2 and figure 6.10. So basically they have this patient and they inject a certain amount of dye into them, and depending on the concentration of the dye, they can tell whether the person has some type of heart problem because they know how the dye is supposed to dissipate over a certain amount of time. So you're still going to use the idea of the rectangles. You want to find the height of the rectangles. But because this is one where you have a real world collection of data, you are going to estimate what the height is of each rectangle. We know the width is 2 because all of the measurements were taken 2 seconds apart. So you would actually go through and estimate the height of each of those rectangles, add them all up, multiply by 2. That's going to give you your milligrams per liters times seconds, and then you're going to use the fact that there was 5.6 milligrams of dye injected, and you're going to come up with a liters per minute measurement. Typically, a healthy person has a liters per measurement around 6, so that's what you're going to be aiming for to figure out if your patient is healthy. So again, that's on page 275. You can go through and read up on that. This section, I am going to try to add some Khan Academy videos because this is really our introduction into integrals. We're starting off with some definite integrals, really looking at the geometry behind drawing these rectangles and splitting these spaces up. You can also always count blocks to get an idea of whether your estimate works or not. And I'm going to stop this now since we have a video coming in. Watch this, contact me if you have any questions.